Hello, this is Greg Wagner with the 7th lecture for CSCV 471, Artificial Intelligence at the University of Arizona. So today's class is going to go over logic agents, which is covered in Chapter 7, Sections 7.1 to 7.5 in the Russell Norberg textbook. And logic agents are a little bit of a pivot from what we've done before. So the model that we've been going through the whole time is you have this environment, the sensors take it in, and then you have a black box here in the middle that performs some logic on the input and then performs some action. And for the kind of the search models we've been using, we have actions, and we have an initial state, and then a goal set. So what's going to change for us is when we use logic agents, we're going to basically use a different type of paradigm. So logic agents kind of try to do with kind of thinking about what how ideas are represented. And a lot of this stuff is also very similar to stuff if you take a formal logic class in a philosophy department. This might be some familiar to you, or if you took a discrete math class in college. And so humans can know things and reason. So how do you represent like knowing things? How are things stored? And the reasoning, how is knowledge stored? So you have these concepts, how do you store them and to solve a problem, and also as you learn more knowledge, how would you do it? So knowledge and reasoning are important for artificial agents because they enable successful behaviors difficult to achieve otherwise. So basically, if this happens and this happens, do this. It's kind of a way we kind of interact with the environment generally and how we think about things. And so we're going to go, basically this course is going to be called knowledge agents, but you might also use the term KB, which stands for knowledge base, or KR, which stands for knowledge representation. And when I took artificial intelligence in grad school, the class was called intelligent machines, but basically the whole class was on the concepts we're going to cover in today's lecture. You can write thousands and thousands of papers on how to represent this language, and I'll touch on it later, but the language Prolog is used to kind of represent programming language Prolog, which you can download for free and play around with, is used to represent logical agents. So kind of to get you started, I want to just kind of talk about this kind of concept. So kind of these kind of links of knowledge and like representation. So if a unicorn is mythical, then it is immortal. But if it's not mythical, then it is a mortal animal. So if a unicorn is either immortal or a mammal, then it is horned. Then the unicorn is magical if it is horned. So can you prove that a unicorn is mythical? Well, how would you do that? How about is it magical? How about if it's horned? How would you represent that stuff? So you have to kind of build up a knowledge base to represent those things. Define what mythical is, define what magical is, define what horned is. And from those you can kind of back your way through and define these things. So for a knowledge-based agent, we have our environment feeds our sensors and the actuator modifies the environment, but our black box, our knowledge, is a knowledge base. A knowledge base is basically a connection of basically a representation of like constraints and logical elements to represent particular data sets. And so for a knowledge-based agent, agent must be able to represent states and actions. So how would you represent a state, like we did with the search problems? How would you represent action? And then incorporate new precepts. So if you see something new, how would you represent it? How would you make it logical representation? So back to the unicorn example. Oh, you see it as a horn. How would that change your understanding of it? And so updating the term representation of the world. So you keep on updating this knowledge base as you gain more knowledge, but you basically have a logic built around it. And if you don't see something, you're going to have to deduce it. And then also deduce appropriate actions. So to give you an example of what this kind of means is, back in the 1800s, you probably heard of Charles Darwin, and he was sailing around South America, and he kind of came up with the idea of evolution because he saw lots of different animals there, and he wrote a book that was very famous. Well, one of the observations that Darwin saw was he saw a meadow in Argentina, and there was these little creatures that had short little ears, and they hopped around. But they didn't look quite like rabbits, which he recognized from England. They looked like other types of animals, but based on the idea that this is a field, this little animal that hops around, that these were probably very similar to rabbits or fill the same niche in the environment. Now, so maybe, if you took a picture of it, you say, oh, this is not a rabbit, but it was a type of hare, it was a type of rabbit that filled the same niche. It just looked totally different than the rabbits he saw in England, but he uses knowledge to do that deduction. So that's kind of what we're saying is, you may not have all the information, but you have lots of different parts of it, sometimes called ontology, that you can represent stuff. So we have an inference engine that represents the domain-independent algorithms, and we have a knowledge base that's domain-specific content, and we're going to combine those to make a knowledge base. So this is kind of the formalization of the pseudocode, and so we have an agent that perceives something and returns an action. And so we already have a knowledge base, and then we have a counter indicating time. So what we're going to do is, okay, I'm going to make a perception, and then add it to the knowledge base, and then ask the knowledge base, based on what I see at this time, what am I going to do? And then basically you're going to tell the knowledge base, okay, perform this action, and then step forward. So basically the idea, what this is saying is, see something, then do something. So the type of knowledge are, we have procedural, these are functions. Such knowledge can only be used in one way, by executing it. So we have this knowledge, what we're going to do with it. Then we also have declarative, constraints. Can be used to perform any different sorts of inferences. So we have these constraints, and from there we can do particular type of inferences. So to give you an example of these different types of things, we're going to talk about something called the Wumpus world. So the Wumpus world is you're trying to get as much points as possible. If you find the gold, you get 1,000 points. If you die, you lose 1,000 points. Every step you take, you lose 1 point. And if you use an arrow, so to shoot like the Wumpus, you're going to lose 10 points. So you want to minimize the use of arrows, and you want to minimize the use of steps to maximize your score. So, and then the environment, these are kind of big constraints. You have a square. If it's adjacent to the Wumpus, it's smelly. So for example here, this little blobby thing that looks like Grimace from McDonald's is the Wumpus. And then you have these little stenches, you have the smells around the area. And then the squares adjacent to the pits are breezy. So if you see a breeze, you're going to mean you're near a pit. If you sense glitter, if and only if, that means there's gold in the same spot. So if you see glitter, it means you're in gold, and you basically win your points. If you shoot the Wumpus, if you're facing it, so if you move up and you see the Wumpus, you can shoot it. But if you're not looking at it, you might be able to smell it, but you can't shoot it. Shooting only uses up 1 arrow, and you're guaranteed to kill the Wumpus. Grabbing picks up the gold if it's in the same square, and releasing drops the gold in the same square. So the actuators are turn left, turn right, forward, grab, release, or shoot. And then the sensors are, you can sense a breeze, you can sense glitter, and you can smell. And so to go into more details, the textbook has better examples. The reason why I bring this up is because I want to kind of show you how you'd build a knowledge base and how you'd actuate on it. So the characters of the world, we have what's observable. It's partially observable. We only have a local perception. We basically only know what's happened with our own square. It's deterministic. Yes. Outcomes are specified. It's episodic. No. They're sequential at the levels of action. So based on what you do, you're going to get different sequences. It's static. So the Wumpus and pits do not move. It kind of makes this little game easier. It's discrete. Yes, because there's only a certain number of squares, and there's only a single agent, which is yourself. So you're not competing against anything. So in this Wumpus world, we can sense that, okay, we know our agent's here. We know this space is okay, and this space is okay, and this space is okay. Why is that? Because we don't feel a breeze, and we don't smell anything. So we know at least these two are okay. So if I go into the next step, I'm going to move forward. So I feel there's a breeze. So what kind of inferences could you feel if there's a breeze? You would know there's a pit here or here. because you feel a breeze, but you're not sure where it's going to be. So your pit, you have unknown knowledge. So what could you do to gain that knowledge? Where could you also sense the pit? You could also sense the pit here. So what you do is you backtrack and say, okay, I smell something, but I don't feel a pit. So I know in this case there's no pit here, but there could be a Wumpus here, and there could be or there's nothing. This place is probably okay because I can smell something, but I know I didn't smell anything over here. So I know there's no pit here. The pit's up here, and there's no Wumpus here. So this space is now okay. So I know the Wumpus is here because I didn't smell anything over there. So I have a pit up here. So I'm going to move up to this spot. I don't smell or see anything, so I know this is okay. So I'm going to move to this spot. So I smell something because the Wumpus is right there. I feel a breeze, so I know there's going to be a pit either here or here. And I sense gold. I see something glitter, so I can pick up the gold. So the idea is if you don't have all the knowledge, you can move to different spaces and sense the different types of knowledge. So there's kind of some sticky situation that you can get into. So if I felt a breeze, if I go back to this original case and I felt a breeze here and here, that wouldn't define anything. There could still be a pit here, there could be a pit here, or there could be a pit here. So there's no safe action. So if you had to do an action, you would maybe go somewhere. Think about when you play, if you've ever played the game Minesweeper, sometimes you just have to kind of take a leap. You don't know if there's mines nearby, but you kind of just have to get going. And in this case, I smell something, but I don't know where the Wumpus is because I don't have any more information. So you kind of have to, you get stuck somewhere, you may not have, it's because you basically get kind of put in a bad position. And so to build a knowledge base, this consists of sentences in a formal language. So basically saying, okay, I have this formal sense of logic. How do I build it? So in this language, it has syntax, means the sentences are well formed, and also has semantics, meaning there's meanings to the sentence. And so there's truth of each sentence with a response to the sense of the world. So in kind of the English terms, syntax means the sentence, if you have correct syntax, the sentence is actually kind of has, like in English, would be noun, verb, object, or noun and verb, or subject and object, or something like subject, verb, and an object. But you may have the correct syntax, but it may not make sense. So you could have a sentence that is, the frog is, I'm trying to think of some adjective that wouldn't make any sense. The frog is toad, or that's not a very good one because the frogs can be toads. A frog is snake. That sentence is syntactically correct, but it doesn't make any sense. Where semantics makes the sentence a sense. So if I say the frog is a toad, that makes semantic sense, and it also is syntactically correct. And so for the examples of this, you have, in basic math, you'd have 6 plus 2 is greater than or equal to 7. This is a seventh because it makes it syntactically correct. If you have 2x plus y is greater than, but no other action, this is not a sense because it doesn't make syntactically correct. And so other examples would be, and then this would be true, then semantically this would be correct if x plus 2 is no less than y, whereas you could also define it as in x equals 7 or y equals 1 or something like that. In other words, this wouldn't be semantically correct if x equals 0 and y equals 6, or something like that. So logic is a declarative language, meaning the assert sentence representation of facts that hold that hold true in the world W. And so these sentences are given a value of true. You can deduce true, false of values of other parts of the sentence. So basically, we're going to assign different values to different variables, in essence, either a value of true or false. And so sentences are semantically correct and that with aspects about the world W, and they hold a representation. And then sentences entail sentences, basically give meaning to other sentences. And then the semantics of the sentences explain more to you about the world. So as you can build on the sentences, it can go into the world to make a little bit more sense to this. I'll give some further examples in a few minutes. And then if the sentences continue to be true, the logic in the world will continue to be true. And so you may have seen this before, especially if you took a discrete or formal logic class before. To connect the different parts of this symbols, we have a kind of a new set of tools. So we have this kind of L-shaped thing is a not symbol. This upside down V would represent and. This kind of V would represent or. This means if then, and this means if and only then. If and only if. And so the way I remember these symbols is I can kind of remember the if one and if and only if pretty easily, just because it means that this implies and this implies exclusively. This symbol I had a hard time remembering. The way I remembered it is if you ever take a set theory class, a U means union, which also is a symbol similar to or in a set. So I remember this V kind of looks like a U, so it's similar to a union. And then if you remember from set theory, the upside down U, so it's basically not a U, it's an and, represents a intercept, which was similar to an and. And then we also have propositional symbols, P, Q, and R, etc. So if we use uppercase letter, it means this symbol represents a value. And basically in the P, Q, and R, we can store the values as either true or false. And so an atomic sentence is basically like a final sentence. So a sentence can be either atomic sentence or a complete sentence. Atomic sentences are basically a propositional symbol, then true or false. So P is true, F is false, or something like that. Or so you have P, true or false. Like a complex sentence is where you can combine multiple kind of declarations. And this is called the Backus-Naur form grammar of sentences. And so, for example, this would be an appropriate one where we have P or Q. If P or Q, then R. Or if and then B or not C would be the way you would read this out loud. And so the orders of sentences are not, and, or, if then, if and only if. So this sentence would be not A or B, then C. You could also represent this as if you didn't know the precedence, would be not and in parentheses or B in parentheses then C. And so you can't do something like this though. You can't do and then B then C. Basically, you have to have kind of a basic correspondence. So for the model would be assignment of every truth value, true or false, to every atomic sentence. So every atomic sentence you're going to assign a value. And then so these are examples of atomic sentences. Like A, B, and C be propositional symbols. Your set would be A equals true, B equals false, C equals false, D equals true is a model. However, this would not be a model if you have M prime, A equals true, B equals false, and C equals false, because you don't have all the symbols being assigned. So that you don't have the D here. M would be a subset of, M prime would be a subset of prime, but it wouldn't be a model. And then with n propositional symbols, one can define 2 to the n models. And the semantics of propositional logic, or PL, specifies how to determine the truth of the value of any sentence in model M. The truth value of the sentence is if the truth of the value is true, is true. The truth of the value is false. The truth value, what this means is, I mean, obviously it is, but something is going to, if a model is true, it's always going to be true. You really can't negate it. The truth value of each atomic sentence is given by M. The truth value of every other sentence is obtained by recursively by using truth tables. So what are truth tables? You've probably seen this when if you ever took, basically going through your programming logic. But we're using the formal symbols here. So we have the propositional value A and B. So not A. If A is true, it's going to be false. False, false. If it's not, it basically negates it. We have true A and B. So if A and B is true, if A and B are true, then this statement will be true. If one of them is false, it's going to be false. If either one of them is false, it's going to be false. And remember, for OR statements, only if one of them has to be true, it's going to be true. And then for the implies, or the if statement, if A and B are true, then this is true. If A is true but B is false, this statement is going to be false. If A is false and B is false, the statement is going to be true. Basically, it's saying if A is true, and then B has to be false, or you can say if A is false, B can be true because B is still going to be true in this case. And then if and only if both statements are true or false, then it's true, but if not, they'll be false. So for the implies, the only time this would not be true is if the second element is false. Implies B, or A if B, as if A is true, then claim that B is true, otherwise make no claim. So in the case odd 5, if odd 5, then the capital of Japan is Tokyo. First, you want to find out what the part of this is. So you have to break down the left part. So you break down this and get the truth for this. So you get this. So what is this first part? If not A, so A is true, so that's false. So A or B is false, and then C is false. So this side here is false. But if A or D, so D is true and B is true, this side would be true. So when I do this, this is false. Now this statement is false since both not A and B are false. This statement is true since both of these are false. This statement is true since one of them is true. And so this is true. This statement is true. So if a sentence S is true in a model M, then M is said to be a model of S. So this correctly represents this space. So we have a very small knowledge base, kind of just based on like car stuff. So we have this representation. If the battery's okay and the bulbs are okay, then the headlights will be working. If the battery's okay and the starter's okay, and you don't have an empty tank of gas, your engine's going to start. So if your engine starts and you don't have a flat tire, it means your car's okay to go. And so the sentences 1, 2, and 3 of the background knowledge is for the assignment for this week. Basically, you'll be building kind of a different kind of build up a knowledge base. And then so 1, 2, and 3 are basically your constants, your background knowledge, and 4 or 5 are your observed knowledge. And so you can let your knowledge be a bunch of sentences, and then your model M is the model of the knowledge base, if and only if it has a model of all sentences in the knowledge base. That is, all sentences in the knowledge base are true in M. So KB is satisfiable if and only if it admits at least one model, otherwise unsustainable, meaning if you have multiple models, it's not going to be satisfiable, I mean. So this statement is KB1, P is some value, Q and R, this is satisfiable. Why is that? Because these are basically mutually exclusive. And then if not P or P, this is satisfiable. Why? Because these both values are the same thing. So basically it's saying P. This is not satisfiable because it basically says, okay, everything's going to, it's contradicting each other. So when you do the assignment, how to define satisfiability, it's basically saying make sure that your model does not contradict itself. And the 3 satisfaction problem, so the 3 sat problem. So you have n propositional symbols, P1 to Pn. Your knowledge base consists of P sentences in the form of QI or QI or QJ or QK, or I is not equal to j or k, these are indices, and qi is equal to p1 or not pi. And so basically saying is you have three different symbols, is it satisfiable? And this is hard to prove, but it is an NP-complete problem. So basically you say you have all these different definitions, you have to check to see if it's satisfiable, which is pretty complex. Basically what you do is you check what the values are for these three symbols, and then basically kind of make a table and see how they're related to each other. So the logical entailment is knowledge base is a set of sentences, and then alpha is an arbitrary sentence. So KB entails alpha. It's basically written as KB, this sideways thing with two lines, as alpha. So KB entails alpha if and only if every model in KB is also a model of A. So if you grab a sentence, you can basically set it up. So KB entails alpha is written as this. Alternatively, KB entails alpha if and only if KB and not alpha is unsustainable, and then KB imply if KB, then alpha is valid. So basically, you have the knowledge base, but if your arbitrary sentence is false, then that sentence is unsustainable or unsatisfiable. And then so logical equivalence is the two sentences alpha and beta are logically equivalent, written as alpha 3 lines B, or alpha is equivalent to B, if and only if they have the same number of same set of models. So A is equivalent to B if and only if A implies B or entails B and B entails A. So for the example, is basically all your models have the same sentences. So you could do this. A or B is equivalent to B or A. A implies B or is equivalent to not alpha or beta, or not alpha or beta is equal to, or is equivalent to, not alpha or beta, and you have not alpha or beta is equivalent to not alpha and beta. So these are examples of logical equivalences. So basically, you can always replace a sentence with an equivalent one in a knowledge base. So if you see this, you can kind of mess around with it until you can get the equal representation. And so we have these inference rules. We have the inference rules. A gamma and psi implies phi consists of two sentence patterns, gamma and psi called the conditions, and one sentence pattern, phi, called the conclusion. So if gamma and psi match the two sentences in the knowledge base, then the corresponding phi can be inferred according to the rule. So what this is saying is if these two things are true, then you can infer the third thing. So for the examples, if you have these arbitrary sentences, alpha implies B, or alpha, if alpha then B, and alpha infers B, then you can replace this with the gamma symbol, this with a psi symbol, and this with a phi symbol, and this would mean these sentences infer the other sentences according to these rules here. So to imply this, so if our batteries are okay or our bulbs are okay, then our headline works. The battery's okay and the starter's okay, and you don't have an empty gas tank. The engine starts. The engine starts, and you don't have a flat tire. Your car's okay, and the battery's okay, and the bulbs are okay. So what would these values be? This would imply. So you have this. This is an atomic statement. So you have this, which would infer that your headlights are going to work. And let me back up a little bit. So to go back, well, I'll just go forward all the way. And I forgot to define this. Modus Ponens means kind of like the way of proving something. Basically, this is saying, okay, if this something if this happens, so in this case, if you know your battery's okay and your bulbs are okay, your headlights work, your modus ponens is saying, okay, I have this this is happening, so I can prove this is true. So if my battery's okay, my battery's okay, my bulbs are okay, my headlight's probably gonna be working. And then so the modus tolenis basically is if something you can prove, basically proving something by proving the negative. So in this case, if my engine starts and I don't have a flat tire, my car's okay. So with the modus tolenis means okay, if something's not going to happen, it's not going to be true. So if I don't have a flat tire, my car's not okay. What does that mean? It means I either my engine's not starting, or I have a flat tire. And so it's basically the negative of this. So that my car's not okay, it's going to be the negative of this. It's basically saying, okay, my engine's not starting, I don't have a flat tire. And these two statements would be equivalent. So I can imply, if I say, okay, if my car's not okay, it either means one of two things: that my engine's not starting or I have a flat tire. And so for other examples include alpha B implies alpha and B, or alpha and B. Alpha and B implies alpha and B implies other. This is just another implication. That implies infers. So you can do inference proofs. So to do inference proofs, you have a set of inference rules and then a knowledge base that's a set of sentences. So the inference is a process of applying successive inference rules from I to the knowledge base, and each rule adding its conclusion to the knowledge base. So for the example of this is we have a set of rules and assertions. So the battery's okay and the bulb's okay, your headlights are going to work. Your battery's okay, the star's okay, you don't have an empty tank, the engine starts. Your engine starts and you don't have a flat tire, your car's okay. So that means your light works, your battery's okay, your starter's okay. Alright, the assertions are your lights at work, your battery's okay, your starter's okay. You don't have an empty gas tank, but your car's not okay. So we know the battery's okay and the starter's okay. So that meets this criterion here. And we know the battery's okay, the starter's okay, and we don't have empty tail gas, so that's 5, 6, and 7. The engine starts, so we know if those are true, the engine's going to start, and so if the engine does not start, or we have a flat tire, that means the car's not okay. So that implies, since we have this engine doesn't start and we have a flat tire, that implies that we have a flat tire. And so we have a flat tire. And so an inference rule is sound if it generates only entailed sentences. So all inference rules that are previously given are sound. So basically the modus ponens is for this: alpha implies beta, alpha infers beta. So basically what its soundness is saying is we have basically something is sound if we use the prior rules to define it. And so for the cognitive symbols, just as a refresher, this horizontal line with two vertical lines is the logical entailment, and this horizontal line with one vertical line is an inference. And so if the knowledge base has a logical entailment to alpha, if and only if the knowledge base implies alpha is valid. And so this following rule, basically, if you have this following rule, you're saying, okay, I have this modus ponens, but that doesn't infer alpha. So this is not a sound statement. So if you have the rules, but you're referring something, basically saying if you're referring something that you haven't proved or haven't shown the rules for, it's not sound. And so completeness is defined if every entailed sentence can be obtained by applying some finite succession to these rules. So basically every entailed sentence, if you use the rules above it, it's complete. And so the modus ponens alone is not complete. But if A implies B, so basically it's saying if A implies B and not B, it doesn't mean that it doesn't mean A is false. It means it can still be true. And so the proof of a sentence alpha from a set of KB sentences is a derivation of sentence alphas, arbitrary sentences, applied to a series of sound inference rules. So the idea that we did before is we found out that we have a flat tire based on the fact that everything about our car is okay, except it wasn't okay. I mean, everything about the car was all right, except we had a flat tire implies we had a flat tire. So how do you do proof? You have a series of sentences and you have an inference. The knowledge base has, if you have a set of sentences, a knowledge base and an arbitrary sentence, will the knowledge base have a logical, basically logical equivalence to the alpha, and that should be true. And so so there's basically a few ways to do this. We have a deduction, or we have a satisfiability test. So the knowledge base has a logical equivalence if and only if knowledge base and not alpha is unsustainable. And so hence, if you're deciding whether a set of sentences entails another sentence or not, or testing whether a sentence or sentence is satisfiable or not, these are closely related problems. Basically saying if a sentence entails another sentence or it's satisfiable, these are basically are very similar problems. And so there's a couple computational approaches. We can do enumeration models, or we can do a construction of a proof. And so basically, if you enumerate the models, and then you also do construction of proof to do this approach. So you build a model up, and then you construct it. So the enumeration of models is the set of propositional symbols given knowledge base but not arbitrary value, and then the size of this propositional model. And so basically, you keep on just building up the model until you can basically prove it. That's what you need to do a complete sentence, and that's what this pseudocode down below is saying. For the satisfiability of the constraint satisfiability problem, so remember we did the n queen problems? You can actually use logic. You can do this on logic as well. And so if you use a propositional symbol of a variable, and the domain is all the variables, so it's either true or false, and the set of constraints is the rules that you have on it, knowledge base without an arbitrary sentence, you can do a satisfiability test. So basically we're building from the last lesson of the CSP as one of the ways to prove a knowledge base. And then you basically use recursive backtracking CSP techniques and heuristics when applicable as far as doing a satisfiability test. And so we build up a proof, which we did using those examples before. And then what do we need? We need a complete set of sound, so a sound set of rules, and a complete search algorithm decides which rules to apply and which ones to which sentences. So basically, if we want a complete knowledge base, we need to also know what sentences we need to apply to build it up. So when do we use this type of logic to do kind of like AI, basically? When you have a large knowledge base, so you basically a lot of different rules, and these can be explicitly made. So think about one prime example they use for these knowledge-based type of problems, these logic access problems, is diagnosing, like medical diagnoses, because you have a set of rules, and you can do a bunch of tests to prove these things. So is this happening or is this happening? Is this person from this genealogy or this genealogy? Do they have these histories? You can make a set of rules to determine what type of illness they have. And you can basically form this problem with a set of constraints. And then you also, you have these tests. So is their blood cholesterol high? Is their triglycerides low? Stuff like that. And so the example we use from the beginning of this is the Wumpus world sentences. And so we basically, how do we figure out where the pits are? So we have a set of rules, a set of sentences here where we have let Pij be true if there's a pit in it, and let Bi be true if there's a breeze. So we can imply that we're going to get a breeze in 1-1 if there's a pit in P12 or P21, and there can also be a breeze in 212 if and only if there's a breeze in P11 and P22. And we know that there's not a pit in P11 and there's not a pit in P11, and there's a breeze in 211. So we can figure out where the pit is going to be. And so the pit is actually going to be where? It's going to be in P22, or I'm sorry, in P12. And then, so we build up a simple knowledge base based on our principles, and then we can define where this test is. And so we have these rules. There's not a pit in P11. We have rule 2, rule 3, rule 4, and then we add up these constraints sentences, build up these constraints, and then we can assume that the pit is actually in P12. So this is a simple way to build up a knowledge base. Basically, you set up a set of rules, and then you add them together. And then build a simple knowledge base in code. Basically, all you need to do is you basically determine what it entails. So you have the kind of knowledge entailment, and then also just check to see what rules are implied. So to read the bottom line here, the kind of the blast out, every known inference algorithm of proposal logic has a worst case complexity exponential to the size of the input. So basically, as you increase the input, you have all these different paths that I can go down, because you have both true and falses for each of the cases. And then we have a lot of rules for logically equivalent stuff, very similar to arithmetic. We have commutativity, these next two lines, associativity, a double negation, contraposition, implication elimination, biconditional elimination. We have two De Morgan's rules, and then distributivity. You can pause it and look over these rules. We're not going to get into too much, but I just want to let you know that if you get into more logic stuff, there is these commutativity rules, and you use these to solve proofs. And so for the reasoning patterns, is you're going to apply the inference rules. You're going to try to find a Modus Ponens, where you do derivatives and elimination. This is basically the Modus Ponens, and then you apply De Morgan's rules. And so we have these different kind of reasoning patterns again. So the idea is, for an elimination, you have the Wumpus ahead and the Wumpus alive. A Wumpus alive, if it's Wumpus alive, the Wumpus alive can be inferred, and this is kind of the most important thing. And then, whether a sentence is A implies B and A, then given the sentence B can be inferred. And basically what this is saying is, if you have a Wumpus, for the example is, if a Wumpus ahead and it's a Wumpus alive, and you shoot, and the Wumpus ahead and the Wumpus alive, you can basically say, okay, if there's a Wumpus ahead and a Wumpus alive, I can shoot. I'm gonna make sure I'm gonna kill the Wumpus because it's gonna be there. And so here's an example by proof before. So we have our knowledge base is we have two sentences, B22, if and only if P12 or P23 or P12 or P33. Observation, not P22. So basically, for the inference of sentences, the entailing sentences, we can use the we'll use the bidirectional elimination to get this derived statement, and then we know that we have P23, and we can eliminate some stuff because we know that this is false, so this whole statement must be false, and since it's an and, we want this statement to be true, so we can eliminate this portion, and then we can plug in we do the basic implementation, we do the counterposition, we can know this is true, and since we know this is not true and we imply it, basically we eliminate P2, and so we have these rules, then we basically say it's not in P1, it's not in P2, it's not in P3, not in P4, and so basically it's saying there is no breeze. We eliminate all the rules. So using this deductive inference, is it sound? Yes. So basically, deductive inference is applying rules until we get all the possibilities eliminated. It's complete since we know that as long as it's not infinite space, but we have infinite limited rules, we may leave something out. So basically, this completeness is saying it's probably complete, but you can't be 100% sure. And then monotonic is as you add more and more rules. If you already have a proof, it's just not going to negate it. That's what I say when it's monotonic. Is as you add more rules, once it's been proved, it doesn't make it worse. So using a resolution type of proof, resolution allows for complete inference mechanism, search space using only one rule inference. So you're given a rule and you want to conclude one thing. So basically, if you think about the proofs you did like in geometry or when you took discrete math, you're given something, you're given some information, and you're given a conclusion, and your idea is to work through it till you get to the conclusion. And so basically you want to get rid of all the extraneous symbols until you get to the proof that you're looking for. So for the Wumpus world, so say there's a pit at, we know there's a pit given information at 2, 1, 2, 3, 1, 2, and 3, 4. But there is, or one of these statements, and there's no pit at 2, 1. Therefore, by resolution, the pit must be at 2, 3, 1, 2, or 3, 4. So it's basically saying since this eliminates this one, these other three are the possible cases. That's how resolution, you try to eliminate different things. And so you can repeatedly apply resolution until there's no new clauses to be added, so the knowledge base does not entail other things, or you have an empty clause. So basically you're trying to prove stuff by contradiction and trying to get rid of stuff. And so this kind of, to apply resolution mechanically, facts need to be conjunctive normal form, which means they're in a format that we can start negating stuff. So to carry out that proof, we need to have a search mechanism that will enumerate all possible resolutions. And so basically, we set up something, and then we basically try to prove it. So we have this is the same example as before, but instead of trying to come to different conclusions, we basically want to do different proofs. So we want to see if the previous statement was actually true. And so given this statement, we're going to eliminate the if and only if based on the double negation, or the negative inference, double inference, and replace implications with the symbols, and then we move inwards to get rid of different parts. So we have this statement and this statement, apply a distributed law, and then we have these 5 different clauses. So given this, we want to prove that the pit is in 1, 2. And so basically, okay, we're going to keep on going. So we have, this is our what's given, and this is on the right's what we have as a proof. And we kind of start eliminating stuff as it goes. So we can eliminate that P is not in 1, 2. So this negates that. And so our next statement is, we're given this. So we have, this is the above statement we got rid of, and we can negate this because we have P1. This is what was given. So next we can go, what's our proof? So we got rid of our proof. Now we get what's given here. So we got rid of P1, 2. We'll get rid of this portion here. Go to the next part of our given. Get rid of this one here. Get rid of see this here. Get rid of this one here, and then our last given statement is this. So it's basically saying, okay, we proved that the pit is in 1, 2. The resolution example, I haven't seen a whole lot, but it's used in code because it's kind of do by programming languages, because it can do back inference pretty well. And so the evaluation of the resolution proves resolution is sound because resolution is true to all its classes. The resolution is complete, so it's a little bit more simple than the previous one by the inference, because we can actually all cases can be completed. And but the resolution, like as before, it grows exponentially as we add more items, it keeps on growing. So the horn clause is a CNF clause that has exactly one positive literal. So we basically have one positive statement. This is the same format that Prolog uses. Prolog is a programming language used to generate knowledge bases. When I took AI in grad school, this is the only language we used. Basically, so we only focused basically on these logic agents. I didn't know until after I graduated that AI, you can do AI in a lot of different ways other than just knowledge representation. So the positive literal is the head. The negative literals are the body. So in Prolog, we define it as we have the head and the body of the body. So basically, in English, we want to prove the head, prove the body, and then the implication is if we can prove the bodies, then we can prove the head. So usually what in prologue you do is you'll define a head, and you define some axioms that keep on going down, and then you keep on adding to the bodies to the head until you can make a final proof. And then so the horn clauses form a basis of backwards and forward chaining. And the reason why horn clauses are nice is they're linear in size based on the knowledge base. So basically, the size of the knowledge base, you're not going to get exponential growth using horn clauses. And so what forward chaining is for each new piece of data, generate a new fax until the desired fax is generated. So basically what the forward chaining is doing is data-directed reasoning, which means that as you add new facts, you're going to keep on rebuilding the list. Backward chaining is whatever your goal is, prove the goal, and then to prove the goal, basically go back from the goal until you get to all the proof statements. And so example of forward chaining is we have this knowledge base, and it's defined by this tree. You can see here P implies Q, so that's that arrow here. L and M imply P, and so we have L implies P. See where the arrows are going. M implies P. We have B and L imply M, so you can see this direction is going this way. A implies A and P, so it goes this way. A and P implies L, so that's going to arrow this way, and then we know that we have defined A and B. So we're basically, for forward chain, we're going to stop down here and then work our way up to Q to make sure that Q's goal is. So we're going to go backwards. We're going to go back up the. I'm sorry, not to say backwards because it's confusing as a backward chaining, but we're going to go up the knowledge base to make sure that all these statements are valid. So we start here. We know that A and B. We validated L in this case. So the number of links basically defines. So we know we invalidated L, so we know L is true. We invalidated M, so we know M is true. We invalidated P, P is true, and then we know Q is true. So this is forward chaining, where basically we start with our data and then we add more data. We work towards our end proof, or prove our statement. Backward chaining is going to go the opposite way. So we have our goal and we want to work backwards till we get this. So we go backwards through the chain, validate the values, and then as soon as they're proved to be true, and then we can basically say, okay, everything else is true. So forward chaining, again, is data-driven. Basically, it's, as you add information, you're kind of just proving the things that they are. Backward chaining is goal-driven, so given this, we kind of go back. Given our goals, we're going to go backwards. So for example, how do I start my car? With my keys. Where are my keys at? On the keychain. Where's the keychain at? That would be kind of goal-driven. You want to say, how do you start your car? You're going backwards. If we do forward chaining, I'd say, okay, I'm going to grab my keys from the keychain. And then I'm going to start my car. So as you add more information for this one, or add more data, in this case the keys represents data, you can start moving forward. And so computers are really good at doing backward chaining. And so backward chaining is used a lot for knowledge bases using computers because they can do it much faster than you would with forward chaining. Basically, you get the goals, and then you get a chain backwards, and if it's not a valid chain, the computers will say, okay, this is not valid, you need to add more axioms, or you need to add more statements, or something like that. So I know this was a complex topic. The main thing that you want to take away from this is, for the next assignment, you want to be able to understand the satisfiability of particular statements, as well as being able to do a proof, trying to expand out as much as you can the data. That'll be the next assignment for this. But the main idea is to get your concepts across of and oring and different types of logic proofs.